we do now? We should do an example. What I would love to do is keep this up on the board and then do an example where I can continue to refer to this, but no such luck. So I shall kill this and now do one example of this algorithm in action. And this is going to be so hard to fit on this board, and I'm going to be very sad about that. Okay, so, and this is the kind of thing, you're going to do a couple of these for homework. So let's take a particularly, like, obnoxious example. So just take A or B star C or B C star. And remember, the precedent is it's like star first, then concatenation, then ORing. So I'm kind of used to this now, right? So the star is attached just to the C. The BC is now like kind of an expression. Here, the parentheses override that precedence, so that's a thing which is being starred and concatenated with C, and then this OR, there's sort of implicit parentheses around everything to the left of the OR and everything to the right of the OR. Okay, we go! This is going to be, why did I clearly hate myself if I'm going to be doing this right now, but alright, too late. Okay, well, what I'm going to now show you is in full tedium. I'm going to show you the recursive construction of a machine that represents this regular expression. Okay, let's go. Well, I'm going to have to write kind of very small here. So first of all, I have this A machine. What is A? Or rather, well, just kind of start going. I've got this machine, and it's going to only accept the character A, nothing else. So it looks like this. I don't think there's anything more to say about that. I also have a machine B. And what does this machine B do? It accepts only the string B, nothing else. So I'm just going through the recursion. Okay, and then I have a machine, I guess I'll do it over here. Then I have a machine A or B. What does the machine is? How can I write a machine which represents the A or B regular expression? Well, as I outlined in the video, I'm going to do S A or B, and that then I will lambda 2. So I will lambda 2 the start states of the previous two machines. So just mindlessly following this algorithm, we see that this is the A or B machine. Okay, I got an A machine, I got a B machine, I got an A or B machine. Now I need a C machine. So let's do that. So what's the C machine look like? Well, okay, it's just like this. And okay, so building these up recursively, I now want to make an A or B star machine. Okay, that's going to be kind of hard and therefore fun. What does the A or B star machine look like? Well, it's a machine which has a start state. That start state is, let's label it S, A, or B star. And there it is. What does this machine do? It lambdas to a new, it has a single lambda to whatever was the start state of the S, A, or B machine. So here we have S, A, or B, the start state of this machine, and what we do in the algorithm I just erased is we start this machine here, we automatically make it an accept state so that this machine will accept the null string, and we lambda to what was the old start state of the machine that we're starring. And then, mostly, we just copy that same machine. So here's SA, here's SB, here's what was an accept state, and we leave it an accept state. And yeah. Okay, but now, if it's really going to be the A or B star machine, then we have to allow for an arbitrary number of A or B's. So we have to allow for this machine to process A or B, but an arbitrary number of times. And the way we accomplish that is by adding more lambda transitions from every accept state of the A or B machine to this point, so that we can run this whole thing back again. Okay, some amount of board management needs to be implemented here. So that's that, and that's that. Okay, good. Now what? Now I need to concatenate to the A or B star machine a C. I can do that. And what happens if I do that? Well, I just do it, man. I just now perform the concatenation operation. So, okay. Oh my gosh. Well, it means I have to do this thing all over again, basically, right? But do not fear. This will end. So here is A or B star. It's going to be an accept state, and we do this. Oh no, sorry. This is a good time to revisit the algorithm, which says if the start state of the S or B, if the start state of the sort of left machine is an accept state, which in our case it is, I think that's why I picked this example, then remove its accept state status, because of course we need to also make it through the C machine. So I hereby take this machine, I remove its accept state status, and now I just mostly now just copying this machine. So S, A or B, I have no plan to like succeed here. Board management wise. Alright. And now here's F, A, and these, so these were also accept states. So I hereby remove their accept state status. That's part of the algorithm. Yeah. Maybe it was better to just draw the entire thing first before I started talking. So here is the entire A or B star machine, just copied completely directly from what happened over there. And now I really only have to do one thing. I take this machine, this one, I take the C machine, which is right here, I stick this freaking C machine like right here, and that's the start state, that's C, that's the accept state of this machine. And now I join these two machines together by doing the following. I add a lambda, I remove the accept state status of every state in this machine on the left, so 1, 2, 3, and I lambda from those 3 states to the start state of the machine on the right. Okay, and so I need now a lambda from here to here, a lambda from here to here, and finally, I think I'm going to do this. Finally, a lambda from here to here. Okay, and so I claim that this machine does the job, and I think I'm just right. Okay, basically, loosely speaking, to be accepted by this machine, you have to make it all the way through this machine one way or another, and then make it through this machine. Okay, so now we have constructed recursively this whole thing Okay, now I need to make BC star and then OR them all together. All right, you can't stop me. I will do it. And okay, what should I do first? Oh, I need to make C star. Okay, how? Trying to be strategic here, but okay. So what does the C star machine look like? It's going to take the C machine, but first create a new start state, SC star, which should be an accept state, and then lambda from that start state to what was the start state of the C machine, and keeping the same accept state, just adding a lambda transition from that accept state to what was the start state. And I think it's very clear that this is, well, I just followed the algorithm, but it's also intuitively clear that this is the machine, that this represents the machine C star. Okay, almost done. Now I will represent the machine BC star. Well, how am I going to do that? I just make a new, I just take the B machine and I just perform concatenation on it with the C machine. So, okay, I think I can squeeze this in right here. So here's the B machine, has this as a start state, and then it goes to B, and then there's this accept state, but that accept state of the B machine should no longer be an accept state because I need to make it through C star. Instead, I take this C star machine, right, which is right here, cha-cha, cha-cha, and okay, I need to fit this, so I gotta write small. Okay, so that's C, and yeah, that's lambda, and that was the start state. So basically, that's what I do, right? No, sorry. Okay. Cha-cha. Okay, so what just happened? I took the B machine, boom. It had a certain start state. That becomes the start state of the compound machine, BC star. I remove the accept state status of the accept state of the machine on the left. I lambda automatically to the start state of the machine on the right. And then I just copy the machine on the right, and the accept states of the overall concatenation machine should intuitively be the accept states of the machine on the right. So that's it. Okay, so now I put a purple box around this, and okay, so what have I done now? I have created this machine, and now in my final act, okay, I guess even I'm not crazy enough to really do this, and I also don't have enough space, this is getting really boring. So I'll just kind of cheat. On the last step you can cheat because it won't get confusing, and I'll just, well, I guess it will get confusing in a kind of a way, so I don't know, I haven't decided what I'm going to do just yet. Let's see. I'll have my start states, maybe I'll make it all the way down here in the corner or something. And what is this start state? Well, it's going to be labeled with A or B star C. I think that's what this was, right? This should have had that label. Or B C star. In other words, I label that start state with the subscript of that state is the entire regular expression. And well, what does it? I guess I can do this kind of big picture style or something. What am I supposed to do? I need to accept the string if it makes it through this machine or this one, and so I will just do that, right? So here is what we might very well have called, and in fact maybe I should relabel this as BC star over here. So I take the BC star start state, and then like things are going to happen. Let's not worry about it. But it's going to end with some accept state somewhere, and that's going to be that. and here I'm lambdaing from here to here, and here is going to contain the S, A, or B star C start state, and it's going to end however it ends. It has just one accept state as well. Okay, so cheating because I have no space, and this is also terrible, I'll just kind of put a rectangle here or something and a rectangle here to indicate, yeah man, just insert without modification. I think that's true for the OR machine. Yeah, just insert without modification this entire machine here and this entire machine here, and that is the machine which does this. Okay, there are obviously many opportunities for pruning this machine, but that's sort of not in the spirit of the fact that this is an algorithm. If this is an algorithm, then the best way to do it actually is kind of just mindlessly and recursively. Though, for short strings, you might think, hey man, can I just use my brain and just essentially just write the machine for my own understanding? Yeah, of course you could always do that, but that's against the spirit of the exercise, which is to master the algorithm. And the algorithm is recursive, so we just follow it kind of mindlessly. And okay, all right, what have we accomplished? What we've accomplished is the demonstration that for any regular expression, there is a non-deterministic finite automaton, and hence a deterministic one, which will recognize precisely the language generated by that regular expression. Okay, the last thing to do to complete the theorem, the big theorem of the week, is to show that every machine can be converted to a regular expression, and that's what we'll do now. Bye.